Yes, so finally we showed that the curvature can be expressed in terms of velocity and acceleration of a particle. If a particle is moving along the curve, along this curve R, then the curvature of this path can be expressed in terms of velocity and acceleration at a given time. Yep. So which is given here. So right now we are talking about this practical problem. So if a particle is moving along this famous helix curve, right? So what is the curvature of that helix curve? Yeah. So using this formula, we can find the curvature of this helix function. Yep. So what was that? Yep. So V velocity cross, you have to take cross product of velocity and acceleration. Yep. So how do you find the velocity? Yeah, differentiate this. Yep, path. So once, yeah, when you differentiate once, you get velocity. Twice, you get acceleration. And take the cross product of these two, yeah, you get this. And find the magnitude of that, yeah, find the magnitude, yeah, which is this one squared, this plus this one squared plus this one squared, which is this, right? Divided by velocity, speed q, yeah, magnitude of this is the speed and q, yeah. So curvature does not depend on the parameter t or time. So the curvature of a helix curve is constant at any point in the on the helix path. Yep. So how is the magnitude of equal to k? Yeah, this one. I think we showed that one here. So this is the original equation here. So rate of change of unit tangent vector along the path. So this is take the magnitude of that. So this is the original. So using this, we express curvature in terms of t here, right? So curvature can be expressed in terms of t. So what is that? Yeah, first derivative of unit tangent vector, and you have to take the magnitude divided by r prime. R prime is velocity, magnitude of velocity, right? So curvature is magnitude of t prime divided by magnitude of velocity. Got it? Do you understand that? Yeah. Yep. So now I use this formula to compute the curvature of a function, two-dimensional function, right? Y is equal to f of x is a two-dimensional function. Now I use this relationship to compute the curvature of that function, right? So yeah, so this time, yeah, R. So we write this one in parametric way, right? So yeah, so this is x coordinate. When x, I write t instead of x, right? And the corresponding y is f of t, and there is no z coordinate because we consider two-dimensional curve function, right? Right. So this is my path. Now, when I apply this formula here, so first find the velocity. Yeah, how do you find the velocity? Differentiate r with respect to t, which is 1 comma f prime comma 0. Yeah, this is velocity. And how do you find the acceleration? Differentiate r twice with respect to t. Yeah. You differentiate twice, you get 0 f double prime comma 0. Yeah, take the cross product, right? You can find that, right? So which is this one. Then you simplify, yeah. So you know how to find the cross product, right? Yeah, for three-dimensional vectors, yes. And take the magnitude of this. Magnitude is this one, right? Square root of 0 squared plus 0 squared plus square root of f double prime. So square root of f double prime squared, which is modulus of f double prime. Yeah. And what is the denominator? Denominator is velocity squared. Yeah. Yep, velocity is 1 comma f prime comma 0 and take the magnitude, which is speed. Yeah, 1 squared plus this 1 squared, 0 squared. Yeah, we don't need to consider, yeah, to the cube. Yeah. Yeah, this is the curvature for two-dimensional, yeah, curves. So this is sum of here. So we can use this formula to find the curvature of these. Yeah. So let's find the curvature. So we apply this. So double derivative of this one is 2 divided by 1 plus this one. So when you change x, so this is the original function x squared. So this is how the curvature changes. Yeah, so you can see the maximum curvature of this function happens at around 0 here. So when you move away from the 0, you get this very low curvature. This is same. Yeah, this is same as the straight line when you move away. Yeah, so curvature, you can see the large curvature around the origin. Yeah, so this is another one, sine function. Yeah, so this is how the curvature changes for sine function. Yeah, so curvature here is the maximum at pi over 2. And again, we are reducing, something like this. Yeah, for ln curve, so this is the curvature change. For this arctan function, arctan or tan inverse, so this is the curvature formula. So when you plot this on the graph, so this is how it changes. Okay, makes sense. So you can find curvature for two-dimensional, so these kind of functions, right? So you can find if you have a function, you can plot the curvature of that function. Got it? Using this equation, this equation, basically this one. All right, makes sense. So remember, I showed that t and t and t dot t prime is equal to 0. That means t and t prime is perpendicular, right? Okay. Then I can define another unit normal vector, unit vector using t prime. So here we have t. So this is t. And t prime is perpendicular to t, right? Perpendicular this side to that side. Don't know the direction exactly. Yeah, if I define n as t prime divided by t prime divided by its magnitude. So this become another unit vector, which is normal to t, right? Yeah. Yeah, one guy is asking, is that coming to prove in the exam? Yeah, I think, yeah, this is important, right? Yeah, this part is very important for your exam. So go through this one. Yeah, that's why last time I briefly explained this part, right? This time I, yeah, thoroughly explained. So, yeah, so I didn't explain last time. So this time I took much time to discuss these things. Yep. Still taking time to discuss these all things. Yeah. So this part is very important, right? Good question. Yeah. Yes. So if you define t prime divided by its magnitude, yeah, so we get another unique vector, and this vector is perpendicular to this unit tangent vector, right? Okay. So this, yeah, so we denote, yeah, so we don't know the exact direction, and I think direction in this direction, I think if you find, yeah, you will realize the direction to this curve bar, yeah, like this, yeah, yeah. So this is n. So n can be expressed in terms of s variable like this using chain rule. Yeah, and can be expressed in terms of S or T. Got it? So, yeah. So N and T are perpendicular, right? Perpendicular to each other. And magnitude of T is one, we know that, which is a unit tangent, yeah. And magnitude of N also one. The way we define N, yeah. So it is equal to one. Yes, yeah. So they are perpendicular. Because the dot product is 0, right? So n points to the inside of the curve, yeah, in the direction the curve is turning, yeah. All right, the curve is turning, yeah, in the direction. The point, so you can find the direction of n now. So you have to find the direction the curve is turning, yeah. So okay. All right, so how do you calculate this unit normal? This is called unit normal. This is called unit tangent. Okay. So this is your famous helix curve, right? So let's find the unit tangent as well as the unit normal vector to this. For this famous helix function, helix curve, right? Yes, yeah. So to find the unit tangent, you know that you have to calculate the first derivative of this divided by its magnitude, which is this. Yeah, we computed that. So how do you find the unit normal on differentiation of unit tangent? Yeah, differentiation of this one, which is this. Yep, and take the magnitude. Magnitude is, yeah, magnitude is a over square root of this thing. Yep. So then you are able to find this unit normal vector, which is negative cos of t, negative sine of t, comma 0. Yeah. So this one is normal to unit tangent. These two are normal vectors. The direction of n, the direction of point, how do you find the direction? Yeah, the direction the curve turns. So if you plot this one, you will realize, I don't see my screen is a little bit dark. Can you see this graph? Yep. So if you look at this, so this is this? Yeah, this is helix function. This is your famous helix function, f of x. So I will send this link to you to play with this curve. Yep. So everybody, so this is the link. I think you can. I will explain this later. Yeah. Okay. Can you explain distance from plane to plane? Oh, you are asking good questions. Don't know. Distance from plane to a plane. That does not make sense, right? Plane to a plane. If two planes are parallel, then you can talk about the distance. If they are not, they intersect at a straight line. Okay. Sure. Let me discuss this one. Then, and if I do this part, then we are done. Yeah. So I will answer to that later. Okay, kembali mau. Right. So, all right. Now I am going to this. So this is very important, right? This is another important part. So let me explain this to you. So we are going to find the components of the acceleration in the. So we are going to find two components: tangential acceleration as well as the normal acceleration. Now, normal component of acceleration. Another one is the tangential component of acceleration. Let's find how do we find. Let's see how do we find we find these components, two components, right? Okay, so we know that v can be expressed in terms of unit tangent vector, right? So velocity is, so these two, unit tangent and velocity have the same direction, right? So you can get velocity, you multiply its magnitude, multiply unit tangent with its the magnitude of velocity. Yeah. So this makes sense. Okay. Yeah, this one also makes sense, right? T unit tangent. Yeah. Yeah, magnitude of this one is the speed. Yeah, ds by dt. Yes, that makes sense. All right. So now I put, so acceleration is rate of change of velocity. Yeah, that we know that. Everybody knows that. Yeah, I put this bit here into the, so t ds by dt. So I use product rule. So this is a product of two functions. Yeah, product rule. Yeah. dt by dt times ds by dt plus t times double derivative. Right, this one. Okay, and so this can be expressed in terms of s variables. So because we have a curvature, look at the original. Let's look at the original definition. Yeah. So all right, here. So here we go. Yep. Yeah. So that is equal to so this is k. Yeah, this is your magnitude of v. Yeah. Yeah, this one here. Let me check that. Right, this is all right. So this can be expressed in terms of ds. Did you understand this one? I didn't see. This is velocity, no speed times. This is dt. Yeah, I didn't see that. dt. Chain rule. Yeah, chain rule. Just chain rule. Yeah. So chain rule, right? Yes, this is chain rule, and times ds by dt. This one and this one here. So we know that the speed is ds by dt. Yeah, you can replace that. Yeah, what is this? Yeah, you can. Yeah, so yep. And wait a second. Yeah, this is okay. And how? So this is, yeah, this one is magnitude of v squared. Yeah. And dt by ds. Let me check dt by ds. So what is the definition of n? Right, dt by ds is equal to normal vector times curvature. Yeah, I substitute that. Normal vector times curvature, v squared. Yeah, so this makes sense. And here we have this. All right, here we go. So the acceleration can be written as the normal component of the acceleration and the tangential component of acceleration. So this is the tangential acceleration and this is the normal acceleration. So does this make sense? Yeah, let's go to a real problem. So if a particle is moving along this circle, right? So then we can find the tangential acceleration as well as the normal acceleration, right? So this is called tangential component of the acceleration. This is the normal component of the acceleration. Okay. Normal component. This one is same with this. Okay. Right. Okay. Let's find this. Yeah, because K has another formula here in terms of acceleration and velocity. There are a lot of so here. So K can be written in terms of velocity and acceleration. So we can substitute this one into there. Yeah, here. So then when you simplify this, you get, yeah, this one. So this is the normal component of the acceleration. Okay. So let's take an example. Okay. A particle is moving around this circle. The center is the origin and the radius is r. With this angular velocity omega, okay, omega is the angular velocity, and then find the tangential and the normal components of the acceleration. So how do you find the normal and the tangential acceleration? Yeah, so we can use this formula to compute normal and tangential components. Okay, so we are given the curve, so two-dimensional curve. Yeah, then we can find the velocity of the particle at a given time, which is this first derivative of this. Okay, and at the same time we can find the speed, which is ds by dt. Yep. So which is a constant. It is this one. This quantity does not depend on t. Then when you take the second derivative, when you differentiate this, this one with respect to t once, you get 0. So the double, d squared s by dt squared is equal to 0 because there is no time term here. This is time independent quantity. So therefore, d squared s by dt is 0. That means the tangential component of the acceleration is 0. So when a particle is moving along a circular path with the radius r and the center is 0 with the angular velocity is omega, there is no tangential acceleration. Tangential acceleration is 0. There's only one component acceleration acting on this particle, which is a normal component. So let's compute normal acceleration if a particle is moving along this circular path. Okay, let's compute. So let's find, for that you need to find velocity as well as the acceleration. Yeah, you can find the velocity by differentiating these ones. Yeah, this is velocity, acceleration twice. Yeah, what is acceleration? So this one, curvature. Yep, so this one, if you have v then, and take the magnitude, what is the magnitude of this? Magnitude is omega r. Omega r is the magnitude. Speed of the particle is omega r, right? Omega r squared. Take the squared. And what is the curvature of a circular path? We know that 1 over r, right? So 1 over r, So curvature is 1 over r. We showed that. Remember, we computed the curvature of a we computed the curvature. I don't remember. Curvature, here we go. So 1 over r. 1 over r. Substitute those things in. Take the equation, then we can get, so this is the normal component of the velocity. Tangential. Let me check. Tangential is 0, normal is this. This should be a normal component. So when a particle is moving along a circular path with a constant velocity, angular velocity, then the acceleration is entirely in normal direction. So orthogonal to the tangent vector or velocity, tangent vector. So does this make sense? Go through this one. I think time is up. I think I will explain the latter part next week, right?